Similar triangles is the topic of the new chapter which we're going to deal in the session. The word similar is something which is quite new for the branch of mathematics here in this part of similar triangles. So what is similarity? How do you define that mathematically, or how do you understand similarity to the most simplest meaning of its understanding? So what is similarity? A similarity is something which we see in similar because the word similar means they are same or representing the same. So if I take the general meaning of similarity, similarity is representing as same. In general sense, we call similarity as representing as same, but in the other form of understanding, we say that similarity is where two different objects look similar, but they are not equal in size. Say, for example, I take a small cricket ball, and then I take a huge football. Then I say that these two objects, the one which is a cricket ball and the one which is a football, are similar. The symbol for similarity is this. So we say that the two objects, cricket ball and the football, are similar. So what makes me define the two objects to be similar? Why not a cuboid? Or when I take a dice and say, why not a cricket ball is not similar to a dice which we use in the games? Etc. Why is that a cricket ball is similar to a football, and why is it that either of these two objects is not similar to a dice which is thrown in the game of Sudo? The reason is these two objects are said to represent similar, but I don't have any similarity between these two objects, because when I take the first two objects, they are round in shape. They are said to be, though not in equal size, but they are both round in shape. Therefore, my round in shape is what is understood through the similarity of the two objects. This is not round in shape, so I say these two are not similar, or these two are also not similar, but these two are the similar objects. So similarity in general sense is understood as the objects which represent as same. Say, for example, I take a very small triangle, minute, and I say a very large triangle. Then these two triangles are said to be similar, but there are some mathematical properties which are included in identifying whether these two triangles are similar. So when I take the concept of triangles, similarity is identified through their angles, the corresponding angles which need to be equal, and the sides which must be in same ratio. So we are going to discuss more further in future sessions on how these two triangles are similar based on their angles and the corresponding sides. So different objects have different similarity, which we're going to identify mathematically through the angles and the corresponding sides. But initially, to understand similarity, similarity is the representation of the objects to be same, but not equal in size, but can be with different sizes, but they can be similar. So before we go in depth into understanding of similar triangles or similarity of two objects, I want to come out with a real life example on why similarity is important in mathematics. What is the significance of similarity is more important to understand before we understand the similarity in its more mathematical sense. So what is its significance? Now let's see the significance of similarity to understand similarity in its more definitive manner. So let's see the significance where I connect this with real life example. Once, say for example, Snigdha has gone to an open ground and she found one of the tree there on the ground, a very tall tree. So Snigdha was just on the ground and she stood out here. She just stood here and she was trying to watch. She was just standing here on the ground and she was wondering a very tall tree in the open ground, which was here. So she was wondering what could be the height of the tree. She wanted to measure without actually measuring with the tape, because a very tall tree, it's very difficult to measure with the tape, because climbing that and going to such a tall height would not be an easy task. So she was wondering on how she can find the height of the tree using mathematics. Then immediately she has seen one of her uncle coming out there who was basically very good in maths, and then she was asking him about the same question which has puzzled her, on how to find the height of the tree without actually measuring this with a tape. Then in this case, she was just puzzled, and her uncle looked at her for a while and then asked her to get a small mirror. Then she brought the mirror and he asked her to put the mirror somewhere on the ground here. So she put the mirror here on the ground, and then, so this is entirely the ground, and she placed the mirror on the ground here. And she asked her to start looking into the mirror until this top of the tree, which is until this top of the tree is visible here. So she started adjusting herself in different positions to see where, until she reaches to that place on the ground where she can see this top of the tree on into the mirror. So until she could see this point of the tree into the mirror, she halted there. Now once she got the position where the top of the tree was identified, then she started looking at that top from here. Now in this case, I identified two triangles. One is the right angle triangle ABC, where AB is the height of the girl Snigdha and C is the mirror, where exactly the position of the mirror is where both of them can see the top of the tree, where she can see the top of the tree which is on the other side of the mirror. And DE is the height of the tree. So in this case, I have two right angle triangles. One is ABC and DEC, which are the right angled triangles, such that both of them are related with the common mirror placed in the middle between the tree, between the girl and the tree. Now here I can easily identify that these two triangles are similar. Though they are of different sizes, we understand that these two triangles are similar. Because they are similar, they make us find the height of the tree indirectly using the height of the girl. The height of the girl can easily be measured with a tape, but height of a tree which is so tall is not that easy to be measured using a tape. Now this concept of similar triangles, where triangle ABC is similar to triangle CED or DEC, is what is very useful in understanding the similarity connected with real life. Now why do you think when these two triangles are similar, the significance is so high that this can be applied in real life? How do you think the height of the tree is measured by Snigdha just based on the two triangles being similar, is the biggest question out here. Because when two triangles are similar, it is assumed that each of the angles is same, corresponding angles is same, and the corresponding sides are in same ratio. So when two triangles are similar, denoted with similarity with this is the symbol for similarity, that implies each of the angle, this angle is equal to angle E, and then this angle is equal to angle E. BCA is equal to ECD, and also angle A is equal to angle D, which is 90 in this case. In this case being 90. So when two triangles are similar, their corresponding angles will be same, and not only that, their corresponding sides will be also in same ratio. That is, when the corresponding angles equal, and if I continue here, and corresponding sides, that is, the sides AC by CD will be equal, this side by this side will be equal to this side by this side, that is AB by DE, and that will be equal to the third side BC by EC. So this is how we understand BC by EC. Therefore, the corresponding sides are in same ratio when two triangles are similar, and the corresponding angles are equal when the two triangles are similar. Therefore, when I say the two triangles are similar, there are two important properties I note. One is the corresponding angles are equal and the corresponding sides are in same ratio. The word corresponding is very important, because if I divide this height with this height, I may not be right in my similarity. So corresponding side of the girl is the corresponding height of the tree. The corresponding distance of the girl from the mirror is the corresponding side measured from the mirror to the tree, but not from mirror to the top of the tree. The corresponding side measuring the distance from mirror to the top of the girl is same as the corresponding side measuring the mirror to the top of the tree. This is how we understand the word corresponding. So in this case, the corresponding sides are in same ratio. Therefore, it's very easy to find the distance of the mirror from the girl and the distance of the mirror from the tree using a measuring tape. It is not that tough task that I can measure the distance on the ground, but measuring on the tree is not an easy task. Therefore, once Snigdha measures this distance using the measuring tape and this distance using the measuring tape, and her height also, which can be measured using the tape, because she can be at the most 5 feet or 5.5 feet. So therefore, once she measures her height using the measuring tape and this height, I know the dimension of this and this and this, then this will not be an easy task using this concept. Where if I know the height of this as x1 and x2 and x3, then I can find the height of the tree by substituting here, where my AB is x1 and my DE is something I want to find as the height of the tree. If I take this as h, then this reduces to h. x1 by h will be equal to AC, which is nothing but x2, and my CD, which is x3, on substitution gives me the height of the tree. h x2 is x1 times x3. That implies h is x1 times x3 by x2, which is the height of the tree. So this is how we find the height of tree by measuring each of x1, x3 and x2, x1 being the height of Snigdha, x2 being the distance from mirror to Snigdha, and x3 being the distance from mirror to the tree, which can easily be measured using a measuring tape. And hence, we obtain the height of the tree without actually measuring. However tall the tree is can be done using similarity of triangles. This is the significance of similarity connected with the angles and the ratio of sides. So let's see the definition of similarity how we understood in the previous session about its application in real life. So as we have seen through the previous example of a tree, the height of the tree which was found, we found that the height of the tree can be found by using the concept that when two triangles are similar, the corresponding angles are equal and the corresponding sides are in same ratio, is what is the definition of similarity. So let's start the definition with the basic of triangle because we are dealing with similar triangles. So let's see what is similarity in its mathematical definition. So in this case, two triangles, say ABC, I take two triangles A, B and C and another triangle DEF are the two triangles I take. Then in this case, the two triangles are said to be similar, denoted by this, if the corresponding angles are equal. Now as I have already told you about corresponding in the sense in the respective dimensions, therefore this angle and this angle are said to be corresponding, then angle A is equal to angle D, and then angle B is equal to angle E, this is equal to this, and finally angle C is equal to angle F. Is one property of similarity, and the second property is that the corresponding sides must be same ratio, that is AB by DE must be equal to AC by DF or BC by EF, and then which is equal to AC by DF. This how are the two properties which make the similarity of two triangles. Therefore, the two triangles ABC and DEF are said to be similar under these two conditions. For any two triangles to be similar, this is the condition. These two, condition 1 and condition 2, both must be true. If one of them holds and the other doesn't hold, they are not similar. If this holds and this does not hold, they are not similar. The condition for similarity is that both the angle property and the ratio property must be equally satisfied, and hence we can say they are similar, denoted with this. Now let's see similarity of polygons. Now that we have discussed about similarity of triangles, when do we say two polygons are similar is the biggest question in case of polygons. So when I take two polygons, also the property is the same, because we say two triangles are similar if their corresponding angles are equal and equally their corresponding sides are in same ratio. Same way, for a polygon, two polygons are said to be similar if their corresponding angles are equal and their corresponding sides are in same ratio. Say for example, I take a hexagon. So this is the hexagon I have considered here, and I take another hexagon out here. Then in this case, these two are said to be similar if the corresponding sides, say I mark this with A, B, C, D, E, F, and A dash, B dash, C dash, and F. Now these two polygons, which are hexagons, six-sided figures, are said to be similar in the same manner as we have defined for triangles. And the corresponding angles, angle A must be equal to angle AA dash, this equal to this, and this equal to this, and so on and so forth. Therefore, for these to be similar, angle A is equal to angle A dash, B equals B dash, C equals C dash, D equals D dash, E equals E dash, and finally F equals F dash. Same way, if I take the corresponding sides, then AB by A dash B dash will be equal to BC by B dash C dash, this by this, this by this, this by this, and this by this. So there will be totally 6 ratios which I obtain in this case, proceeding by AB by A dash B dash, and then BC by B dash C dash, and so on and so forth. 6 times getting the ratio. So from this I conclude that whenever I have any n-sided polygon or a close-sided figure, the two objects are said to be similar if their corresponding angles are same, however big the number of angles are. If the number of angles is more, still the corresponding angles must be equal and the corresponding sides must be in same ratio. Then we say the two close-sided figures are similar to each other. This is how we understand the concept of similarity connected with polygons. So what is the difference between similarity and congruency? Now similarity is what we have discussed in the previous session recently out here. Then what is congruency? How are they different? When do we say two objects are similar, or when do we say they are congruent? Or is it that similarity and congruence is one and the same? Is what we are going to identify in the session. So for this, let me take two triangles and identify the difference between the congruency of triangles and similarity of triangles. So before we start with, my definition for similarity says that they are similar in shape but not with same size. So size of the objects are not same in similarity. That is, one of the object as I have taken here is said to be similar to a very big object provided the corresponding angles are similar. But when I take the congruency, I say that they are with same size. So the main difference between similarity and congruency is that similarity may not have the two objects to be with same size, but congruency has the two objects in same size. So when I take the congruency, similar in shape and with same size is what I understand the difference between similarity and congruency. Say for example, I take the triangles, these two are said to be congruent, denoted by this, similarity denoted with this, and congruency denoted with this, are said to be congruent if they are equal in size and similar in shape. But they are similar in shape, but they are not equal in size, is how we understand the difference between similarity and congruency. So how do you understand the difference between similarity and congruency mathematically is very important. So let's attempt on the mathematical understanding of the difference between similarity and congruency. So for example, I take similarity initially with its definition, then I have similarity is already dealt with its definition, and I take congruency out here. So for this, I would take the basic example of triangles, because in this case, I took the triangles ABC is said to be similar to DEF if the corresponding angles are same and the sides are in same ratio. So in this case, let me also take the same triangles ABC and this with DEF. Now here I would like to compare between understanding of the difference of similarity and congruency using its mathematical properties. So in this case, angle A equals angle D and angle B equals angle E and angle C equals angle F for similarity of two triangles. Then I have the corresponding sides in same ratio, that is AB by ED must be equal to BC by EF, that is equal to AC by DF, is what I get for similarity of two triangles. So when two triangles are congruent, let's see what are the properties. Now in this case, angle A is equal to angle D as in the case of similarity. So I get angle A equals angle D, and angle B equals angle E, and angle C equals angle F, is what I get in similarity and congruence to be same. But when it comes to similarity, the corresponding sides are in same ratio, but when it comes to congruency, the corresponding sides are equal, is what we identify through congruency and similarity. In this case, the sides are not equal, but they are in same ratio. But in this case of congruency of two triangles, the corresponding sides are same, even in case of any polygon. Therefore, here I have AB is strictly equal to ED, and I have BC is strictly equal to EF, and finally my AC is equal to DF, is what I understand the difference. And because the corresponding sides are equal, this retains the same shape, but because the corresponding sides are not equal but in same ratio, it does not retain the shape, the size, but it becomes with different sizes. But the sizes are maintained to be same strictly because the corresponding sides are equal. This is how we understand mathematically the difference between similarity and congruence through their respective mathematical properties. So let's understand the most important property in similarity. This is the heart of similarity, scale factor. Now, scale factor defines the similarity, the extent of similarity of the two objects, or especially the two triangles. So what is the scale factor? What is it about that it is so much connected with similarity is the biggest question of the topic scale factor. So let's see the definition of scale factor through similarity of triangles. So let's consider two triangles ABC and A dash, B dash and C dash assumed to be similar to each other. So in this case, triangle ABC is similar to triangle A dash, B dash and C dash. So in this case, as we have seen that corresponding angles are equal for two similar triangles, the definition of this equal to this and this equal to this and finally this equal to this. Therefore, the corresponding angles are equal. Now coming to the second property of similarity, the corresponding sides are in same ratio. Therefore, considering the corresponding sides, AB by A dash B dash will be equal to BC by B dash C dash, and AC equals A dash C dash. Now, as I see that the three ratios are equal in their own means through equality, then this must be equal to a common value, say a k. So the values as obtained for each of the ratio is k when I equate this entirely to k, and this k is called the scale factor. Scale factor is that quantity which multiplies to one side with this. So in this case, this being the scale factor. Now, what is the significance of scale factor? Note, k, which is called the scale factor, decides, or the value of k decides the extent to which the object enlarges or becomes smaller than the original object. So the value of k strictly decides on how much big the object enlarges or how much smaller the object compresses compared to its original object. It's a very important property in geometrical concept of understanding the similarity of two triangles or any two objects through the scale factor. So k decides, or the value of k decides the enlargement or compression of the original object is what we understand through the scale factor. Now, as I see here, what happens when k is greater than 1 or k equal to 1 or k less than 1 is what we are going to see for the session. So let's include 3 cases through which we understand the scale factor connected with the size of the two objects in similarity of two triangles.